kids in calculus in California are like, have you seen the early videos? Those are worth watching. Those are worth watching, man. Don't even go to class. Okay. So we're doing 5.2b today. And there's a new vocabulary word, which I think they slipped into the directions on one of the homework problems. I'm sorry about that. Maybe not. The exact area is called the definite integral. So remember yesterday that huge painful part E? We were finding the exact area when we did that. And that's called the definite integral. So whenever we have exact area, we can just use the term definite integral instead. And the symbol for the definite integral is that crazy looking S thing, which you've seen in your book. Hey, Jonathan, would you mind closing the door? Thanks. Okay, so we're going to do the integral from 0 to 4 of the square root of 16 minus x squared dx. I guess maybe I should start with 1. Math teacher that can't even count to 1. This is ridiculous. Okay, so this looks complicated, but first we're going to focus on the function, which is y equals the square root of 16 minus x squared. So I'm going to try to graph that function, because that's what we're trying to find the area of. So I'm going to square both sides. Then add x squared to the other side. So does anybody recognize that type of an equation? It's the equation for a circle. Since nothing is subtracted from x, and since nothing is subtracted from y, the center of the circle is 0, 0. Okay, so if I'm going to graph this circle, the center is at 0, 0. So if this said x minus 3 squared, then the x-coordinate of the circle's center would be 3. But since it's x minus 0 squared, the center is at 0, 0. Okay, then remember, this is the radius squared. So the radius of this circle is 4. So if I go in every direction from the center, 4, I'll get to my outer edge. And then I'm going to graph that circle. Why did I only graph the top half? No, these are x's. Good guess. These are guesses. These are x's. Yeah. You can have a negative area. Great guess. I like it. It's coming up later. We're going to have negative area in a second. Sorry to scare you. Yeah. if it's going to be a function, it can't have two different y values, right? If I filled in the bottom of the circle, it wouldn't pass the vertical line test. But the key is right here. This is just the positive square root. So that's why it's just the top half of the circle. If you solved this and went backwards this way, you would end up getting the positive and the negative square root. So if you graph the positive square root, that gives you the top half of the circle. And then if you graph the negative square root, it gives you the bottom half of the circle. So Ella's comment is good. If we had the bottom half, it wouldn't be a function. Well, we can tell that it's supposed to be the top half because this right here is the positive square root. Okay. All right, so there's our graph. We're trying to find the area because it's got this crazy looking area symbol in front of it. And we're finding the area from 0 to 4. So that means we're going from x equals 0 to x equals 4. So we're looking for that area. So how am I going to find that area? Well, how do you find the area of a circle? Pi times radius squared, right? And how much of a circle is this? 1/4 of a circle, right? So in order to figure out that area, I'm just going to take 1/4 times pi r squared. If it was an entire circle, it would be pi r squared. But since I'm just doing that fourth of it, it's 1/4 pi r squared. Okay, then the radius of this particular circle is 4. So it's, how's it going, Corey? 1/4 times pi times 4 squared. So 4 squared is 16, then 1/4 of 16 is 4. So the final answer is 4 pi. Okay, now I could have done this instead to find the exact area. I could have done 4 rectangles. And then I could have said, hey, that's not very good. And so then I could have done 8 rectangles. And that would have been better, right? And then I could have done 16 rectangles, and et cetera, et cetera. So if I had done that, I would have done like 4 over n times the sum of a big mess, I equal 1 to n, limit as n goes to infinity, right? I could have done all that. You with me? And we did that once yesterday, and it was painful. And then you attempted to do it once last night, and it was painful. But we could have done that. If we had done that on this problem, we would have gotten 4 pi. Okay? This one, it was tons easier to do it this way because we know how to find the area of a circle. So we can just do it this way. But there's going to be some problems occasionally where you don't know what the area is. So you're going to be forced to use this for the exact area. But certainly, if you can avoid it, you want to avoid it, right? Bryn, you had a question?
Yeah, like if you had made the rectangles, how would you account for like that extra space?
Eventually, the rectangles would have gotten so thin that there wouldn't have been very much extra space at all. In fact, theoretically, they would have gotten infinitely thin. And then there wouldn't have been any error. That's why we're taking the limit as n goes to infinity. Good. Okay. So now, example 2. This is going to be the integral from -3 to 5 of -2 plus x dx. And for part A, we're going to go back to approximating. We're going to approximate using 4 left endpoint rectangles. Okay, so now we're taking a step back and we're going to 2 days ago when we were just approximating instead of finding exact. All right, so this is a straight line, right? And the tricky thing about this one is sometimes it's below the x-axis and sometimes it's above the x-axis. So I need to explain to you, this is brand new for you, what happens when the function is below the x-axis. So far, all the functions we are finding the area of, we just found the area above the x-axis. So when the function is above the x-axis, we're supposed to find the area down to the x-axis, so this area, right? That's what we already knew. Here's the new thing. When the function is below the x-axis, what you do is you find the area up to the x-axis. So it'll be this part of it. And that area counts as negative area because it's below the x-axis. Okay, so the two new things are, if the function's below the x-axis, find the area up to the x-axis, and then that counts as negative area. Okay, so we're supposed to be going from -3 to 5. So that's covering a total space of 8, right? If you go from -3 to 5, the width covered is 8. And we're supposed to be using 4 rectangles, so we need to divvy that 8 up into 4 parts. So the width of each rectangle is going to be 2. So there's going to be a rectangle from -3 to -1, because that's a width of 2. Then there's going to be another one from -1 to 1. I'm not exactly sure where this hits the x-axis. I'll deal with that later. Then there's going to be another one from 1 to 3. And then the fourth one's going to be from 3 to 5. So rectangle here, rectangle here, rectangle there, and rectangle there. Okay, so now let's start with this rectangle, the one from -3 to -1. How am I supposed to find the height of that rectangle? Plug -3 in, right? Why not -1? Because it says use left endpoints, right? So I'm going to plug -3 into the function, and that gives me -5. So that means the height of this rectangle is -5. And so then the area of that rectangle is the height times the width. The width is 2. So we say that that rectangle has area -10, just because it's going down below the x-axis. Okay, now for -1 to 1, I'm going to plug -1 into the function. That'll give me -3. So that rectangle will have a height of -3. So the area will be 2 times -3, which is -6. Then from 1 to 3, I plug in 1, right? That'll give me -1. So that's why it was a little bit awkward there, because it's only going down 1. So 2 times -1 comes out to -2. And then for this one, you plug in a 3. -2 plus 3 is 1. So that one will have positive area. Yes? Yes, but I was told to use left endpoint rectangles, so that's why I'm making it down here for the whole width. I'm just using the height at -1. I don't feel like I answered your question totally. I think what you're concerned about is the fact that this was below, and this was above. But I was told to use this as my height. So it's not looking like a very good approximation is what you're telling me. And I agree with you, but that's what I was told to do in the directions. I think you totally have it now, am I right? Okay, good. Everybody else okay with this? So that adds up to negative 16, if I got enough sleep. Am I okay? Okay, so that was just the approximate area, right? So now for part B, I'm going to calculate the exact area. So to get the exact area, I need to be a little bit more careful with my graph. So if I'm going to graph this line, the y-intercept is negative 2. And the slope is 1. So I'm going up 1 over 1, up 1 over 1. So now I discovered that it hits at 2, which makes sense. So there's my line. So I'm supposed to be taking the area from negative 3 to 5. So from negative 3 to 2, I've got a triangle below the x-axis. And then from 2 to 5, I've got a triangle above the x-axis. So to figure out the area, the total area, I'm just going to add up the area of both of those triangles. So 1/2 base times height plus 1/2 base times height. Okay, this triangle here, the base of it is 5 because it goes from negative 3 to 2. And then how can I figure out the height? Plug it into the formula, which I already did earlier, right? It came out negative 5. So here's the weird thing. This height is negative 5. Why am I leaving the height as a negative 5? Because I want this to come out as a negative area, right? Because area below the x-axis is supposed to be negative. So even though we all know heights can't be negative, we're still counting that as a negative height. All right, and then this one is 1/2 times 1, 2, 3. I didn't draw this to scale, sorry. 3, because it's from 2 to 5. And then this height, I have to plug in 5 into my function to figure out that height. It's 3. So 1/2 times 3 times 3. So that's negative 12.5 plus 4.5. So then the final answer is 8. So Christian's comment really was a good one, right? Because look how bad this approximation is compared to what it actually is. Oh, well, okay. It's still pretty bad. Negative 8's a lot less negative than negative 16. So, and that was because of what she said. She was noticing that, hey, most of this is positive, and we're counting it all as negative. Good. Everybody doing okay? All right. All right, so we're up to 3. And for this problem, we're going to express as a definite integral and then solve. And the problem is find the calories burned when a walker burns 300 calories per hour from 6 to 7:30 p.m. So somebody is exercising, maybe after dinner at 6 o'clock, and they're really gung-ho about it, so they walk for an hour and a half, and they know that they burn 300 calories per hour for that hour and a half. Okay, so we could figure out the answer to this problem really easily. The solving part is a piece of cake, but I'm going to force it to be a calculus problem. That's the little bit tricky problem about it. Okay, so I want you to notice that if I graphed time in hours on the bottom, and then the rate of calorie burning over here. So we're graphing time on the bottom and then the rate that the calories are being burned there. Okay, so what is the rate that the calories are being burned? 300 calories per hour. Does that change? No, it doesn't. It's always 300 calories per hour. That's not really realistic, right? Because probably when you're walking faster and slower, et cetera. But this person burns a consistent 300 calories per hour the whole time. So the graph of the rate is going to be a flat line. The rate is always 300. At 5 o'clock, she's burning 300 calories per hour. At 6 o'clock, she's burning 300 calories per hour. At 7 o'clock, she's burning 300 calories per hour, et cetera, et cetera. It's a consistent rate. Okay, she's walking from 6 to 7.5, right? 7:30 is 7.5 hours. So we're actually looking at this from 6 to 7:30. So the way I'm forcing this to be a calculus problem is I'm showing you that if we take the area of this rectangle, 300 calories per hour is the height, and 1.5 hours is the width. I mean, this is what you guys wanted to do from the very start of the problem, right? 300 calories per hour times 1.5 hours is the right answer. That's what you know to do. But it's also the area of this rectangle, right? So that means that this problem can be expressed as the area from 6 to 7:30 underneath the graph of 300. So when the problem says express as a definite integral, that's what they're looking for. They're looking for you to write it as an integral. And then, of course, the answer is 450 calories, right? Okay, now in the last problem, we had negative area, right? And you all were thinking, that's crazy. Well, let me show you that in this problem, negative area could make sense. So this person is walking, right? And they're burning 300 calories per hour. But then they stop walking. And so they're not burning as many calories. And then they sit on the couch. So they're not burning any calories. And then what happens? They start eating, right? So they're not burning calories, they're gaining calories. So then the gain of the calories would be negative, right? Because you don't want that. And the burning of the calories would be positive. And then if you took the whole area, you'd figure out what happened throughout your whole day. Did you eat more than you burned, or et cetera, et cetera? So that's why the negative might make sense. Okay. All right, we got one more problem. Okay, so this problem is kind of a contrived problem that is good because it talks about the meaning, but basically there's a homework problem like this, and so that's why I'm doing this problem. There's some value to it, but it's a little bit strange. Okay, so we're going to express as a definite integral just like we did on the last problem. This time we're going to have this crazy notation, limit as n goes to infinity of the sum I equal 1 to n of 1 over ck times change of x on the interval 1, 4. It'll get a good picture of it then. Okay, so does this look familiar? It's that horrible part E from yesterday, right? Kind of like that. Okay, so the first thing I want to comment about is this right here, the change of x, is just the width of one of the rectangles. A small change in x is the width of each rectangle. Yesterday it was 4 over n. Okay, so this is the width of each rectangle. So what do you think this is? It's the height of each rectangle. Okay, now when you calculate the heights of the rectangle, how do you figure out the heights? Plug it into the function, right? So I think the function is supposed to be 1 over x. That's the contrived part of it. For some reason, they call ck x, and I don't really like that. But the value you're supposed to get out of it is to find the heights of the rectangles, you use the function. And so that's why the function is 1 over x, because that'll give you the height. So here we have the height of a rectangle times a width of a rectangle. Okay, but when you do this, the rectangles are going to get infinitely thin, right? Just like Bryn talked about earlier today. So eventually, when you're doing 1,000 rectangles, they're going to be tiny. So when they get infinitely thin, we don't call them change of x, we call them dx. So dx is an infinitely thin width. Okay, and then all of this says add all of those up. This says add n of them up, but then make n really close to infinity. So how do you add up infinitely many things? Well, we learned the symbol for that today. And then it's on the interval 1, 4. Okay, now I don't know this for a fact, but my brain tells me it's got to be true. Check out this symbol. it could morph into this, couldn't it?
I see it.
I think that's where they got the symbol. They took the summation and morphed it into a weird one that kind of, so that it would be an infinite summation rather than a finite summation. I don't know that for a fact, but I think that's true. Might as well say it's true. And put it on the internet. And then see if anybody argues with me.
So that needs to be on our notes, right? That's very important.
Yes, it's very important.